putting it on YouTube as well. So if those for those who have missed the first lecture, you can always go on YouTube and you can see the lecture from the last time. And so this is going to be recorded. It's going to be up there, and everything, all the links are on my website. Okay, so why don't we begin? Thank you all for being here. I have just wanted to do a little bit of a review ooh, one sec. Files, never mind. So let's do a little bit of a review to talk about ionic bonds and covalent bonds before we jump into anything new. Okay, so here's the periodic table once more. The last time we were here, we had a conversation about how we can use the periodic table to kind of figure out how to draw how many electrons an atom needs to make a bond, right? We talked about two types of bonds. We talked about covalent bonds, and we talked about ionic bonds. So let's just review really quickly. We talked about covalent ionic bonds being present primarily in inorganic compounds, and that's what we're going to see. And really, the long and short of it, we're going to number these columns 1, 2, 3, 4, 5, 6, 7. This is 8. And the idea is that tells us the number of valence electrons that are present on that atom, right? And so that atom has that many valence electrons, and it'll be trying to get to 8. We talked about the fact that the first level requires a 2-electron octet, the second level requires an 8-electron octet, and the third level requires an 8 or 18. And we're going to be focusing on 18. And so when we are trying to make bonds, whether ionic or covalent bonds, we're really trying to get either that level filled or remove that level, electrons from that level, and make it empty. What we're going to see is it's very easy. You can generalize that it's very easy for the metals, these here over to the right, to the left, I'm sorry. It's very easy for those metals to give up electrons so that they can have a filled level. Okay, remember, if you have 2 electrons in level 3, it's easier to give up 2 electrons in level 3 and have a filled second level than to gain 6 more to get to 8. And so these metals are typically going to just lose however many electrons they have. If you lose an electron, you become positive, right? And so because of that, these left 2 columns are what we call our metals, right? These are going to be our metals, and they're going to have a plus charge. Everything in the first column, or group 1, as we like to call it, is going to be +1 because it currently only has 1 electron in its valence. So if it loses 1, it becomes +1. And that's why we always have lithium plus, we always have sodium plus, we always have potassium plus. All of those metals in the first column will be positively charged in order to become the same with the next one. Beryllium will be 2+, magnesium will be 2+, calcium will be 2+. And this is going to be very easy when we think about ionic bonds because that's just their natural charge, okay? They are typically going to make ionic bonds with the atoms on the right side. For example, fluorine. Fluorine needs 1 more, right? So fluorine is always going to be trying to gain 1 electron to become 8. So it's fluorine minus. Likewise, chlorine minus. And you get the idea. Oxygen is going to be 2 minus. Sulfur is going to be 2 minus. So the typical ionic bonds we will see will be between atoms on the left and atoms on the right. And so whenever I see those atoms in a formula, I'm always pretty much convinced that these atoms are going to be ionic bonds, going to make ionic bonds. Okay, now this is organic chemistry, and as I told you in the last lecture, that our molecules are typically going to be covalently bonded. And you can think about it in terms of electronegativity, right? So the ones on the left are not very electronegative, and the ones on the right are very electronegative. The electronegativity is basically the atom's desire to pull electrons to itself. But the ones that are in the middle around here, and even the ones that are to the far right, are typically going to make covalent bonds, right? And so they will interact with each other. Instead of giving up electrons, they will share them, all right? And in the last lecture, we talked about how the sharing works. Basically, you need to make as many bonds as you need electrons to get to 8. So for example, carbon, right? Carbon has 4 electrons in its valence. In order for carbon to really get to 8, it has to get 4 more electrons. Now, it's probably going to have to share typically to get those. And so in order to get to 4, you have to share 1 to get 1. Every time you make a bond, every time you get in a relationship with another atom, one atom brings an electron to the table, to the relationship, and you bring an electron to the relationship. And so carbon has 4 electrons, which means every time it needs to get another electron, it has to share 1. So carbon will share 1 with hydrogen. That is a bond. Every pair of electrons that are shared is equivalent to a bond. That's the definition of a bond. A bond is a shared pair of electrons. So carbon will share 1, hydrogen will share 1, and they will be happy. Hydrogen only needs 2 electrons to become happy, and because it's in the first row. Likewise, again, carbon will share 1 to get 1, it's at 6. Carbon will share 1 to get 1, it's at 7. Carbon will share 1 to get 1, it's at 8. And so carbon finally makes it to 8. Hydrogen, all the hydrogens make it to 2, and there we have it. This is a Lewis structure for CH4. Carbon is very happy it's shared 4, and it's gained the 4 it needed to get to 8. All right, we can do the same thing with oxygen. Oxygen has 6 in its valence. And make sure that you write your electrons as lone pairs if you can. So 2 will always pair up. And so oxygen needs to get to 8, but it has 6, which means you need to share 1 with a hydrogen and share 1 with another hydrogen. And then we can write that as well as 2 bonds. Every time you share, that is a bond. And then it has 2 electrons for itself, okay? So that is a Lewis structure. And every time you see a Lewis structure, right, every atom that is in the second row and the third row should have 8 electrons. So I can count. If I look at this carbon in this molecule again, carbon has access. Remember, every bond is 2 electrons, right? 2 shared electrons. So that's 2 electrons, 2 electrons, 2 electrons, 2 electrons. Carbon has access to 8. And I can check hydrogen. Each hydrogen has access to 1 bond, which is 2 electrons, and that's all it needs. If I look at water, by the way, for those who didn't realize, this is the Lewis structure of water. This oxygen has 8 electrons. It has 2 on top by itself, 2 on the bottom to itself, and it's sharing 2 with a hydrogen on the left, and it's sharing 2 more with the hydrogen on the right. Oxygen has 8 electrons, right? So the goal for us is to draw structures, right, that respect the octet rule that we've come to appreciate in the last lecture. Okay, so let's move on and let's talk about how we can look at a molecular formula and draw the Lewis structure. Because what we've done so far is I've just drawn structures for you. But what if I gave you this, CH4? That's easy, right? We just did that. That one is easy. You can draw that. But what if I gave you something else? For example, let me erase this. What if I gave you a different formula and say, for example, C2H4. What about C2H6O? How do you know what to draw, right? And is there a rule that you can use or a process you can follow to draw a potential structure that would be acceptable for that molecular formula? And so what I'm going to do now is I'm going to teach you how to draw Lewis structures from the formula. All right, so let me open up the notes for that I'm using today. Lecture 2. Here we go. All right, so drawing Lewis structures. So two things I want to say about this process, okay? The process requires, typically, to simplify this for all of y'all, you should really only use this process if you have a neutral molecular formula. And when I say neutral, there are no charges. We haven't done any charges yet. I've stayed away from charges. Everything we've drawn so far has been neutral. We're going to keep it that way for now. So the whole idea is you use this formula or this process with when you have a formula that's neutral, okay? You also want to use this process if there are at least 2 or more carbon atoms in the formula that I give you. It just works out really well, okay? Now remember, these are organic molecules we're trying to draw, which means they're going to have a lot of carbon atoms in them typically. Organic molecules, carbon is the backbone of life, the backbone of organic molecules. So it makes sense that we have a process like this that involves 2 or more carbon atoms because carbon will be overrepresented in these formulas. So why don't we use an example to do it? Instead of just, like going through rules, why don't we use an example? So the first thing I want you to do is to find the total number of valence electrons that are present in the molecular formula. And I've given you an example. We're looking at C2H6O, all right? That is the formula that we will be using for this problem. Can people see this online? I feel like the screen is kind of moving a little bit. Yeah, is it stable? Yes, I think so. Okay. So C2H6O, that's what we're looking at right now. Let's see the number of valence electrons. Now, you want to get good at being able to look at the periodic table. I see someone wrote C6H12O6. We're not ready for glucose yet. But let's try to draw something for C2H6O. So you'll get comfortable knowing the number of valence electrons. You have a periodic table. If you don't have one, I would suggest you just have one on hand. Can someone tell me the number of valence electrons that are present on carbon? We just talked about that. How many valence electrons does carbon have? 4, right? You all are very good at knowing that carbon has 4 valence electrons. So we have 2 carbons and it has 4 valence electrons, right? We then have 6 hydrogens. How many valence electrons does hydrogen have? Hydrogen has 1. Great. So hydrogen has 1 valence. We can do that. And we have 1 oxygen. How many valence electrons does oxygen have? 6. Very nice. You guys are so good at this, right? And eventually you'll just get really good at this. And if can someone add this up? What are the total number of valence electrons present in this molecule? 24. So 2 times 4 is 8. 8 plus 6 plus 6. That actually gives us 20. Wait, that's not 24. I know I can do basic math. That's 20. All right, thank you. 20, thank you. So we have 20 valence electrons. Now we're only going to use this at the end. We don't need this right now. We're going to use that to check what we draw. So let's keep moving. This is a formula you will need to know. This is a very important formula. I'm going to explain what it means. The thing is this, and let me explain why this is important. When you draw a Lewis structure, you don't know if you're just going in cold how many double bonds you have, how many triple bonds you have, etc. Right? And if you just try to draw it, you're gonna more than likely get into trouble. Your single bonds aren't gonna work out. You're gonna get confused and anxious and stressed. You're like, why don't my electrons add up? I'm supposed to have this many atoms. I can't fit them. And so this formula actually is very cool and helpful. And what this formula tells you, it tells you how many double bonds or rings, I'll explain that shortly, that are present in your formula so that when you draw something, you can incorporate those in the Lewis structure. Okay? So the formula is you take the number of carbons you have in the molecular formula, you add 1 to that, and then you subtract half of the sum of hydrogens plus halogens. Halogens is the group 7 elements, X. We represent that as X. So fluorine, chlorine, bromine, iodine. Those are all the atoms that need 1 more electron to get to 8. So basically you're adding all the atoms that make one bond, hydrogen and halogens. And then you subtract any nitrogen atom that is present in your formula. What this means is that oxygen doesn't matter in the formula, okay? It's not very helpful in the formula. You don't need it, okay? It doesn't factor in the formula. So why don't we do that? We have 2 carbons plus 1 minus half. We have 6 hydrogens. We have no halogens in this formula. There's no chlorine, fluorine, bromine in C2860. And we have no nitrogen. So we can just close the bracket right there. Does that make sense? Now, let's calculate this. What is this telling us? This is 3 minus 3, which is equals to 0. This is very helpful because what 0 means is when I draw my atoms connected to each other, it means there are no double bonds present in this molecule. I can draw all single bonds, which makes it very easy, right? So that's the information it's telling you. Now, double bonds are typically how we think about satisfying degrees of unsaturation. And the reason why we call it a degree of unsaturation is it's telling you the fact that instead of making connections to new atoms, things are doubling up and connecting within the molecule itself. And so that can be a double bond, but it could also be a ring. So you can satisfy, if you do the math and you get 1 degree of unsaturation, you can satisfy that 1 degree by either drawing a double bond or you can draw a ring structure. And when I say a ring, I mean you need 3 or more atoms connected to each other in a ring. Okay, we'll do some examples. It'll make sense. So the next thing you want to do now that we have a plan, our plan is there are no double bonds in this molecule, only single bonds, is that you want to start off by bonding your central atoms. Okay, let me move this up. You want to bond your central atoms to each other with single bonds. And when I say central atoms, I mean the atoms that make multiple connections. You can leave the ones that make 1 bond at the end, okay? And so the atoms that are going to make multiple connections are C, N, O, right? Or sulfur, right? Carbon makes 4 bonds, nitrogen makes 3 bonds, oxygen makes 2 bonds, sulfur is below oxygen, and so sulfur makes 2 bonds. By the way, I see a question in the chat. N is nitrogen in the formula. So N is actually the element nitrogen for that question. And so these are atoms that will make multiple connections. And so what we're going to do is we're going to start with them. So if looking at my formula, I have C2860. So I have 2 carbons and I have an oxygen. Those are the atoms in my formula that make multiple bonds. So I'm just going to start by connecting them to each other. The whole point of this is I'm not asking you here to draw a very specific molecule. I'm simply asking you to draw a possible molecule for this formula because there might be multiple ways you could connect these atoms together. But the point is, can you see a formula and can you actually draw something that is legit? So let's do this. Yes, that's the formula, hydrogen plus halogens minus nitrogen. And so let's do it. So carbon makes 4 bonds, but we're not worrying about that yet. I have 2 carbons. I'm going to connect them to each other. And I'm going to connect the O as well. Those are my central atoms. And this is where your knowledge of the number of bonds that atoms make come into play. Carbon makes 4 bonds. So I need to respect that and add 3 more lines or 3 more bonds. So carbon must always make 4 bonds. Okay, I'm going to erase this at the top so that I have space. The other carbon must also only make 4 bonds. So I can draw 2 more lines, 1 up top, 1 at the bottom. Does that make sense? And then oxygen, based on our understanding, only makes, sorry, I'm not going to put that in yet. Oxygen only makes 2 bonds. If you follow the rules, you will never fail. This will always, always, always work out. And so now we have 6 spots for 6 hydrogens. It always works out. And so we have 6 spots. A hydrogen can go there. Hydrogen makes 1 bond. Hydrogen makes 1 bond. Hydrogen makes 1. Hydrogen makes 1. Hydrogen makes 1. And just like that, we were able to draw a molecule, we're able to draw a molecule that respects that that formula. So the last thing we want to do now is we want to put in the lone pairs and multiple bonds as we discussed, if necessary. So why don't you look at this and tell me right now if this is, which atom, I should say, needs lone pairs. So take 5 seconds to do that. So which atom needs more electrons? Oxygen, exactly. So remember, all the atoms want to get 8 electrons. And so carbon, I can see, has 8, and hydrogen wants to get to 2. Oxygen is the only one that isn't at 8. And so that means the oxygen should have 2 electrons, 4 more electrons on it, right? And so that would be the correct structure for this, a possible structure for this molecule. Now, this is where my valence electrons come in. I counted up to 20 at the top. So can we count in this Lewis structure and convince ourselves that we actually had 20 in this molecule? So if we count, we should get 20. Can someone tell me if I have 20? Yes, I do. So I can see it here. I can see hydrogen, right? There are 2 electrons here. There are 2 electrons here, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. I use 20 electrons. This formula is correct and legit. All right. Okay. Can we draw a different arrangement of atoms? Is there another way I could have arranged these atoms? Let's try to draw a different arrangement. What could I have done? Instead of putting the 2 carbons next to each other, what could I have done? I could have put oxygen in the center. There we go. I could have put oxygen in the center. All you children online, let us add then. That was actually bad. Oxygen only makes 2 bonds. Thank you very much. I'm distracted. And so if we do that, then we can get a formula that looks like a structure that looks like that. And once again, oxygen must have 2 lone pairs, which gives it a total of 20 as well. So these are 2 Lewis structures that are both correct for the formula, but these are actually 2 totally different molecules, right? And so it's very important to understand that you can have the same formula, but you can have a different structure. And we have a name for those 2 things. We have a name. There's a relationship for those. We call those structural isomers. If you have 2 structures that you draw from the same molecular formula and the atoms are connected differently, they are what we call structural isomers. They're different molecules but they have the same formula. Okay. And I want to show you a structural isomer, 2 structural isomers that you probably have heard of before, but never really thought about as structural isomers. And this is THC and CBD. Those 2 molecules, right, are both structural isomers. Now, what I've done here for you is I've drawn the lines because the molecule is too big to draw hydrogens, but THC and CBD are structural isomers. They look similar, but if you look down here, there's a connection here. There's no connection in that location for CBD, but all the same atoms are present in both of these molecules, but they are totally different molecules. And so I wrote the definition for you here. Structural isomers are molecules that have the same chemical formula, but they are different arrangements of atoms. Okay, so now what I want you to do is I want you to draw for me a molecule. I'm going to give you a formula. We're going to start practicing. Let's see if this made sense to you. And let's see what you come up with. Everyone's going to come up with different things. Well, let's try to see what you can draw on a piece of paper for the formula C3H6O2. If I gave you that formula, C3H6O2, what would you draw? And then I'm going to choose one person eventually to tell me what they drew. Remember, follow the process. The first thing you want to do is you want to count the number of valence electrons that are in this molecule. And then you want to calculate the degrees of unsaturation. And I will show you how to draw this, yes. But I want you to try. Based off what I gave you as the rules prior on the screen before, you do it. And let me give you the formula for degrees of unsaturation for those who forgot it. It is C plus 1 minus half of H plus X minus N. And X is the halogens. All the other letters represent the actual atoms that they are. X represents the halogens, which is chlorine, bromine, iodine, etc. You don't need the X in this formula because we don't have any chlorine, bromine, or iodine. Okay, I'm going to give you all a few. Oh, I saw someone wrote something in the chat. Okay, come through. That's a nice structure. A little bit, someone is advanced over here. Who is it? The ozone mama. Why don't you draw a different one then? I see Stephen and the ozone mama suggesting the same thing. Why don't you come up with a different formula? Because you could draw something potentially different. All right. So let's walk through this and see what you all came up with. So how many valence electrons? We have 3 times 4 plus 6 times 1 plus 2 times 6. What total did we get here? We got 30. Great. All right. Let's calculate our degrees of unsaturation. That would be 3 plus 1 minus half of 6. And that would give us how many? That gives us 1. Great. Thank you so much. Now, this is different, right? Now we have 1 degree of unsaturation. Remember, you can satisfy this degree of unsaturation either by drawing a double bond, or you could satisfy it by drawing a ring. And what I'm going to do now is we're going to look at a bunch of different ways we can do that. So let me start off with drawing a double bond. So can someone tell me what atoms they want to make a double bond between? Remember, you want to make multiple bonds between atoms that can make multiple bonds. Which atoms do you want to make a double bond between? Okay, I saw someone say a C and a C. So you can just draw that. C, C, double bond. And by doing that, you satisfied your degree of unsaturation, which means everything else you draw can be single bonds, right? Everything else you draw has to be single bonds. And you still need to respect the number of bonds each atom makes. So now let's keep going. Carbon makes 4 bonds. Carbon makes 4 bonds, right? We need another carbon, and we need an oxygen, right? This carbon must have 4 bonds. This oxygen must have 2 bonds. And just like that, we can draw something that satisfies this. If I put my hydrogens in, then I get hydrogen, 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 hydrogen. I have 6 hydrogens in this molecule. I have 3 carbons, and I have one oxygen. And of course, oxygen must have two lone pairs. Whenever oxygen is neutral, it makes a single bond and it has a lone pair. Did anybody draw this exact one? All right. There are two oxygens. Thank you so much. Excuse me. This formula has two oxygens, so I'm not done yet. We could instead put one of them over here. Yes. And we could put one, and then we would have an H to that. Thank you so much. Still thinking about the previous one, right? So this would work. I have two oxygens, six hydrogens, and three carbons. Okay. Can someone tell me a different way? Because there are tons of ways you could potentially arrange these atoms. I see someone said we could do a C double bond O. So let's draw that. I'm going to draw that down here. Here is a C double bonded to an oxygen. It doesn't matter how you draw it, where you point this, okay? So if I have a C double bonded to an oxygen, what else could I do now? Can someone tell me what to do? What do you want to bond it? Carbon must make four bonds. What do you want to do? Yes, two lone pairs on the oxygen. Thank you so much. All right. Okay, I see someone said, I have an O. You could have an O. You could put the H on the O, but you need two more carbons. And that would give you a perfectly good answer. You could have made another arrangement. You could have put a C on that side, a C on this side, and that would give you a totally different molecule. And you get the idea, right? You get to draw the atoms however you want. I see someone said a C double bonded to two O's. I'm glad you suggest that. Let's do that. If I have a C double bonded to two O's, then I couldn't do that. That's actually carbon dioxide. And the reason why I couldn't do that is because I've run out of connections for the carbon. Carbon only makes four bonds. So if I had the carbon double bonded to two different O's, then that's a full molecule. So I have to keep leaving space for the other atoms. I don't want to finish the molecule prematurely. I got to keep leaving space. Okay? Any questions? Does this make sense? Everybody think they can do some more? All right. I have some examples for you to practice, and I want to see what you do. All right, I'm going to start a new page, and we are going to do a lovely problem set. So here's a formula, and I want you all to draw something for this. Okay, so if I gave you C5H8O, so that's C5H8O. Can you draw something that actually satisfies that molecular formula? There is a book for this class. It is on the website, and the link is in my bio on my TikTok page. So let's try to draw something and see if you can do it. So remember, you have 5 carbons, 8 hydrogens, and 1 oxygen. So you need to calculate your valence electrons, and then you can do your degrees of unsaturation, and then you're going to connect all of those atoms together, and that would give you a structure. I see someone said C bond 4 H's. If you do that, that's just CH4, right? And that's a done molecule. You want to make sure you're connecting you have a place to connect all of your atoms. You need to use all of the atoms in the formula. So don't make all the 4 bonds to hydrogens, because then you don't have any more connections to make. Every atom in the formula must be used. Okay, so yes, you can write it in a linear structure if you'd like. I'm going to use this one to do a ring system as well, but let's write a linear structure. So let's move. I think you all can do this. Let's do the degrees of unsaturation. That's 5 plus 1 minus half of 8. And that should give you 6 minus 4, which is 2. Yes? Everybody has that? Great. So if you have 2 degrees of unsaturation, then you must have 2 satisfied. And let's talk about that. If you have 2 degrees of unsaturation, you can satisfy that in 2 ways, or actually multiple ways. You could have 2 double bonds. You could have 2 rings. You could have, oh yes, we'll do the valence electron soon. You could have 2 double bonds. You could have 2 rings. And you could also have a double bond and 1 ring. You could also have a triple bond, because a triple bond is 2 extra bonds. So let's calculate the valence electrons. I'll tell you this much. When you get really advanced, you don't need to calculate the valence electrons. And that's because if you trust the process and you do it properly, it always works out. But the valence electrons, for those who are nervous, is a good way to check your answer in the end. So let's follow properly and calculate now. So for those who are still nervous about this, they can trust that they've drawn the right thing. So that's 5 times 4 plus 8 times 1 plus 6. And that gives us 20 plus 8, that's 28, plus 6, that's 34. So we should have 34 electrons once we're done. Okay. So how do you want to satisfy these 2 degrees of unsaturation? I'm just going to draw something that makes sense for me, and as I said, you might have different answers. So I'm going to do a C double bonded to a C. That's 1 degree. And then we'll draw a single bond to another C. And then I'm going to double bond that to an O. That's my choice, right? You could do whatever you want, but you need 2 degrees of unsaturation. And I chose to make a C double bonded to a C and a C double bonded to an O. And then I still have 2 more carbons, right? I used 3 carbons, 1 oxygen. Remember, you want to use all of your non-hydrogen and non-halogen atoms first. That's the best way to do it, so that you don't leave something out. So you can put a carbon here. Let me be generous and put another carbon there. And that gives me 5 carbons. So that's 5 carbons and 1 oxygen. I've satisfied my degrees of unsaturation because I have 2 double bonds. And so now I just have to respect all the bonds that these atoms make. This carbon needs 1 more bond, this needs 1 more, this needs 3 more, and this needs 3 more. I think all of those atoms are happy. They're making the right number of connections. Carbon with 4 connections each, and oxygen with 2 connections. And so that leaves space for all of my hydrogens. And it better work out to be 8. If you do it properly, it will always work out to be 8. And so 1, 2, 3, 4, 5, 6, 7, 8. And then now I can count my electrons. I need 2 on the oxygen. I always have 2 lone pairs on the oxygen, so it gets to 8. Now, if I add up all my electrons, I should have 34, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32, 34 electrons, right? 34 electrons. I have 15 bonds and 2 lone pairs. Okay. Let us try to draw something in a ring. How could you draw something in a ring? You could imagine putting 5 atoms in a ring. I see Lori saying something about a cyclopentanone. I like that as an answer. And when I say a ring, the smallest ring you can draw is 3 atoms in a ring, right? The smallest ring is a 3-atom ring. So if you have 3 atoms in a ring, you have a ring. If you have 4 atoms in a ring, you have a ring. 5, 6, whatever, okay? So I am choosing to put all of my carbon atoms together in a ring. Remember, I said you can satisfy a degree of unsaturation by drawing a ring. This satisfies one of the 2 degrees of unsaturation. It means I still need another degree of unsaturation. I'm going to choose to do a double bond for the other degree of unsaturation because double bonds are just so easy. I've used up all my 5 carbons, however, so I could choose to make a double bond between one of the two carbons that already exist, or I could choose to make a double bond with my oxygen. You're going to realize that I have a strong preference for double bonds between carbons and oxygens and carbons because they're very abundant in molecules. But I'm going to choose to do a carbon and oxygen again. And so there I have my carbon and my oxygen. The other carbons now need to have 4 bonds. I need to check them. Oxygen is happy. It's making 2 bonds and it has its 2 lone pairs to make it 8. This carbon in the middle here is happy. This one needs 2 more connections. This one needs 2 more connections. This one needs 2 more. That one needs 2 more. And that's the space for me to put my hydrogen atoms. And just like that, I have a molecule. Okay. Do people think they understand this? Does this make sense for people? Okay. I'm not done with you yet because you could draw, and many of you have probably drawn a number of different things. You should be able to check your answers, right? We've talked about this process. It's not going to look like mine because there's so many structural isomers we can draw, right? There are a lot of different possibilities. But as long as you go through and you check it, you can actually draw almost any combination, and you could draw multiple things. So I see a hand up on the Zoom screen. Yes, Grayson, is there a question? You're muted. I might be muted. You can ask a question if you'd like. All right. Well, if not, we're gonna try some more. Let us try another formula. So why don't we do C6? Let's add a nitrogen in this one. C6H13N. So that's C6H13N. Let's see all the different things you can come up with as my handwriting deteriorates. So C16H13N. Will, could you type your question again? I didn't see that. Yes, you would get 2 degrees of unsaturation. One ring satisfies one of your degrees, and a double bond satisfies your other degree. So Amy, you are not. So a carbon that's double bonded to an oxygen only makes 4 connections. So that's still 4 connections, right? It's 2 connections to a oxygen and a single connection to other things. So it's still 4 lines, 4 bonds that are coming out of that carbon. Hopefully that helps. All right, so let us see what we can do. These are also Zoom meetings. You can go to my website. There's a Zoom link if you'd prefer to be in the Zoom. I'm doing it both of them at the same time for those who are asking. I'm also recording them and I'll post them on I'll post this lecture on YouTube. So let's calculate the degrees of unsaturation. I'm pretty confident that my electrons will work out. I'm jumping ahead. 6 minus 1 minus half of 13 minus 1. Remember the formula is H plus X minus N. I have 1 nitrogen, so I have to subtract nitrogen. Be very careful. A lot of times people add, but they nitrogens. And if you do that, then you're honestly going to make an error. So this would be 7 minus half of 12, which is a degree of unsaturation of 1. Okay? So this means you can draw 1 ring or you can draw 1 double bond, whatever you prefer. It's up to you. Okay? I'm going to try to push you all to think about rings because I love rings. So I'm going to draw all of my 6 carbons in a ring. And that satisfies my degree. I'm going to put my nitrogen attached to the carbon, one of the carbons. And so just like that, I've added all of my non-hydrogen atoms or non-halogen atoms. Nitrogen needs 3 bonds. That's nitrogen's bonding pattern. And a lone pair. And then this carbon needs another, and I'm going to put a hydrogen there. That carbon needs 1 more. This one needs 1 more. This needs 2. This needs 2. This needs 2. This needs 2. And that would be an appropriate structure for this molecule. Okay? Oh, somebody did exactly that. I saw that, Amber. Nice job. You could do a double bond as well. Let's throw a double bond in there as well. So you could have done a double bond to a carbon. It's up to you. Do whatever you'd like. You could do a double bond to a carbon. A possible double bonded molecule could look like this: 1, 2, 3, 4, 5, 6 with a nitrogen. And then I'm just gonna respect the rules. This carbon needs 4 bonds, nitrogen needs 2, this needs, right? And everybody should be happy here. Hydrogen, 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 hydrogen. And that should be 13. And nitrogen needs to have 8, so it has a lone pair, okay? And so this is a molecule that would satisfy this formula. And so hopefully you realize you can draw so many different things. And the idea is for you to feel comfortable drawing a number of different possibilities for molecular formula. Now, they're going to be different, right? For example, we just drew earlier two structural isomers. We drew this molecule, okay? And we drew this molecule. And these are really cool because this is ethanol, right? This is ethanol that many of you drink in your booze, right? That's ethanol. And this is what we call an ether, okay? Actually, you might know ethers. Ethers are actually what people use to initially for anesthesia. It was first demonstrated in Boston, where they used it. There's the ether dome is what they call it, where they first demonstrated ether used in anesthesia. So the molecules are different and they have very, 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 very different functions. And so it's important in the future when we move forward that we draw exactly what we mean. Right now, we just want to be able to draw something, and that doesn't matter to us. Okay, so we're going to move on from Lewis structures. And what we're going to talk about now is formal charge. And that's because we need to look at atoms that are not neutral anymore. We've been focusing on atoms that are neutral, and sometimes atoms are going to have a charge. And the question is, how do you recognize when an atom has a charge? And how do you calculate it? And so formal charge really is a really cool concept in organic chemistry, and it really indicates electron ownership. And this electron ownership is really a comparison to how many electrons it quote unquote owns right now. If you consider that it's sharing those bonds, electrons in the bonds equally, compared to how many it had in its natural state. For example, oxygen always has 6 electrons in its valence. It starts off with 6 electrons in its valence, but when it's in a molecule, it might not own 6 electrons. And if it doesn't own 6 electrons, then that means it's going to have a charge. It could be positive charge if it's owning 1 less than it should own, or it could be a negative charge if it's owning 1 electron more than it should own. So how do we calculate it? It's a very straightforward formula. It's the number of valence electrons, which it normally has, minus half of the bonding electrons, minus the unshared electrons. That's just a bunch of numbers and statements. Why don't we just do an example? So if I see a molecule like this, okay, does that oxygen look normal to you? We've talked about oxygen as normally making 2 bonds, right? 2 bonds and 2 lone pairs. But this oxygen is not making 2 bonds and 2 lone pairs. It is making 3 bonds and 1 lone pair. But if you compare it to a neutral oxygen, they both still have 8 electrons. That oxygen on the left has access to 8 electrons, right? If you count the bonds, each bond is 2 electrons. That's 2, 4, 6. And it owns 2 to itself. That's 8. Meanwhile, in the molecule on the right, water, that oxygen has 2 bonds and 2 lone pairs, total of also 8. But although they have 8 electrons, the ownership is not the same, okay? And so this formula helps you calculate the true ownership of the electrons that it has access to. It's like, how many does it really own? And so let's do the one on the right. So what is the number of valence electrons for oxygen? 6. That's never going to change, right? Oxygen always has 6. And then we're going to minus half of the number of electrons, total number of electrons it has in bonds. So how many total electrons does oxygen have access to in bonds? It has access to 4 because it has a bond here and has access to a bond there, which means it has access to 4, okay? So we're going to take half of that. And then we're going to subtract however many it owns to itself, by itself, which are the lone pairs. And that is 4 because it has 2 at the top, 2 at the bottom, right? So that is how we do it. Does that make sense? So it's 6 is its natural state minus half of how many it has in bonds minus 4. And that gives you 6 minus 2 minus 4, which is 0, right? And this makes sense because oxygen, we know, and we've discovered, and we actually derived it, that oxygen just likes to make 2 bonds, and it has 2 lone pairs. That is its natural state. By the way, this formula is a little tricky for some people, so I have a shortcut. You want to hear the shortcut? The way you calculate it is this. It's the valence, right, minus the sticks minus the dots. This is a shortcut way, all right? Valence minus sticks minus dots. So if valence of oxygen is 6, it has 2 sticks coming out of it, and it has 4 dots. So it's 6 minus 2 minus 4. That's the short way to do it. And that's really how you get there very quickly. Okay, the shortcut is even better. I don't like to teach the shortcut first because you need to understand where it comes from, but yes, the shortcut is easy. Okay, so with that in mind, let us look at the one on the left. For the oxygen, right? How many, the valence is still 6. Let's do that. How many sticks? 3. How many dots? 2, which means the oxygen has a 1 or a +1 charge, which means it only owns 5, okay? It only owns 5. It owns 3 and it owns 2. And so that means that oxygen owns 5. 5 from 6 means it's positive. It doesn't own as many as it would normally own if it's by itself, okay? And so this is a positively charged oxygen, okay? Does anybody want to try another one? Do people want to try another one? Let's do another one. Let's see nitrogen. If I gave you this nitrogen, what is the bonding pattern? What is the formal charge, I should say, on that nitrogen? What is the formal charge on that nitrogen? Nitrogen is how many valence? What's the valence for nitrogen? Valence for nitrogen is 5. Yes, if you look at the periodic table, nitrogen only has 5 electrons. Remember, we count from left to right, and that tells us the valence. So nitrogen has 5, and we're going to minus the sticks, and we're going to minus the dots. That means this nitrogen is 0. What I'm trying to show you is you already know the neutral ones. Carbon is 0 when it's making 4 bonds. Nitrogen is 0 when it's making 3 bonds and 2 lone pair, and 1 lone pair. And oxygen is 0 when it's making 2 bonds and it has 2 lone pairs. That's just the natural state. Okay, how about a nitrogen like this? What is the charge Oh, I am so bad. I'm literally jumping ahead. What is the charge? Calculate this on this nitrogen. Does this have a formal charge? You don't need to memorize the periodic table. You just need to have access to it. So you can look at it and see it. I can't put it up right now. If I had it, let me see if I can put it up. What I'll do is on the next sheet, I'll draw you a few more and then I'll put it up for you. How does that, does that work? We'll do that. So nitrogen has a positive charge because it has 5 minus 4, which is plus 1. Okay. So why don't I pull up the periodic table for you all. And there you can see it. Let's talk about it again, right? So you can see this is 1 valence, 2 valence, 3, 4, 5, 6, 7. That's how we know, right? Because each row adds 1 electron as you go across, right? So I can look immediately and see anything that's in this row is gonna have 4. Anything that is this row is gonna have 5. And so that's kind of the quick way. So you don't need to memorize it. You just need to have an access to a periodic table. And if you're taking a course, typically the professor will give you a periodic table, or there will be one in the classroom. Okay, so let's do a few more. Shorthanding these molecules already. This is a little foundational. Okay. All right. So carbon, hydrogen, hydrogen, H. Well, I want you to look through all of these molecules I'm drawing and determine if any of the atoms in the molecule has a formal charge. And I'm going to put the electrons in, by the way, so you can see. You need to have all the electrons in order to do this. Okay, so let's look at each of these, and I want you to see if there are any atoms. I've drawn in all the electrons that are on those atoms, and I want you to tell me if there's a formal charge on any of those. Okay. So let's start with the first one. Is there a formal charge on the carbon atom? The answer is no, because it is making its 4 bonds and it has 8 electrons, right? This oxygen has a positive charge. You can see the formula is 6 minus the 6 minus the dots. That's plus 1. So very nice job. Everybody seems to get that. Let's look at the next molecule. Does any of these atoms, or do any of these atoms require a formal charge? You need a positive charge on the nitrogen atom, okay? The nitrogen atom needs a positive charge. If you calculate it, it is 5, right? Minus the 4 dots, that gives you 1. So the nitrogen is positive. Carbon is neutral. We know that carbon makes 4 bonds, meaning that it's neutral. If we still do the math, it's going to be 0. 4 minus 4 is 0. And then this oxygen looks weird. We haven't seen an oxygen like this yet. So normally I like my oxygen to make 2 bonds, but this one is making 1. And so I'm going to calculate that. It is oxygen is 6 from the periodic table, minus 1 stick and 6 dots, which is negative 1. So we've come across our very first negative atom. Okay. Now you might notice that I'm not writing negative 1 in the circle or positive 1. We typically just write plus and minus. That just means it's one. If it's larger than one, then we'll write the number. Okay, let's look at the final one. I love this one. This one is really nice. Okay, so carbon looks good. Nitrogen is making four bonds. I think I can tell now when nitrogen is making four bonds, that usually means it's going to be positive. Well, you can calculate it. 5 minus 4 bonds is equal to plus 1. The oxygen on the right is good. I'm very familiar with that oxygen. 2 bonds and 2 lone pairs should be 0. And then the oxygen on top, I just saw it again, right? The oxygen on top, I just saw that one. That is a negative. So the whole idea is eventually you'll get very good at being able to tell what an atom looks like when it's negative, when it's positive, when it's neutral, and those are the bonding patterns. And what I'm going to do is I am going to put in the chat, I mean, sorry, in the Google Drive, a nice little document that shows you what they all look like when they are positive, negative, and neutral. So the atoms we really care about are carbon, nitrogen, oxygen, fluorine, and any of them that are below. Okay. And eventually you're going to be really good. And we use boron sometimes. If sorry, boron. And so eventually you're going to become really good at knowing what all of those atoms look like when they're positive, when they're neutral, and when they're negative. Okay. Okay. So this is probably where we will end for today. On Tuesday, what we're going to do is we're going to do functional groups because we need to understand what all of these atoms look like when they're connected together and when they're in a particular arrangement of I should say they have a particular function, right? So for example, what you've noticed, and we've been doing this a lot so far, is when you see this arrangement, right, of atoms, this is what we call a carboxylic acid. Okay. This is an acidic unit. And so what that means is anytime you see that, you know that's an acid. Right. And so we're going to talk about other functional groups, right? Functional groups like an aldehyde. Okay. Anytime you see this particular arrangement, this is an aldehyde. And what's important about functional groups is that they tell you how the molecule is going to react. And we're going to get into reactivity eventually. So we need to learn our functional groups first. Once we learn the functional groups, then what we're going to do, and we're going to do all of this on Tuesday, is we're going to do acids and bases. We're going to do reactions, and I'm going to teach you how to draw arrows because that is very important. We have to show you how electrons move. And once you understand that, you're going to be very, very well on your way to becoming an organic chemist. All right. So thank you all for stopping by. Thanks for hanging out. There's a post survey so I can have an idea of what you all need me to revisit before we start on Tuesday. And I'll see you all then. I'll post this on YouTube. Thank you all. Have a great night.